One of the most accessible forms of circuit racing is improved production car racing. It has some presence in most countries in one form or another. This racing typically involves taking a production car chassis, stripping as much weight from it as possible, and adding basic aerodynamics. When I say aerodynamics, it means a plywood splitter and a simple rear wing or spoiler. A popular car, even in the US, is a small front-wheel drive hatchback. These hatchbacks are usually light and can utilize reasonably powerful motors. The Suzuki Swift GTi is typical of one of these cars, among others like Honda Civics. Though this model of Suzuki may be a little bit old, it still makes sense and has competitors running them effectively today, despite them being almost 40 years old. The rules governing this class of modified production car racing is relatively similar throughout the globe. I will be directly using the Australian version explicitly under the Improved Production Car Racing Association of Australia, Group 3J, Improved Production Cars. The US equivalent is the SCCA Super Touring classes, with the English being the hot hatches. The US classes are allowed a flat floor, which is probably the biggest difference aerodynamically. So the rules state, apart from the minimum ride height, an aerodynamic device can be used on the front and rear. That is, a splitter can be run on the front, and it must not extend beyond the front bumper when viewed vertically. On the rear, depending on the age, this GTi sits on the boundary of 1985. Either a spoiler or a wing can be used. In this case, a spoiler will be used as it has more engine freedoms, like adding a turbo. The baseline of this model without a rear spoiler creates a total of 312 newtons of drag and 194 newtons of lift, with 199 newtons of lift at the rear. Adding the full GTi body kit, the horizontal spoiler specifically made everything better, both lift and drag. Then the rear bumper gets a cutout, again improving everything to produce 268 newtons of drag and now only 51.7 newtons of lift, 80 newtons of lift at the rear. Fundamentally not numbers a race car would want. Adding aerodynamic devices will dramatically improve the performance of this car around a track. In total, 6 configurations will be tested to understand how much each component's addition contributes to the characteristics of the car. An additional case was run to serve as a conclusion. Starting the modifications, an air dam hangs off the bottom of the front bumper, then a splitter is added, a spoiler, followed by modifications to the air dam area, finally a gurney flap. For the most part, each addition has a positive effect for the aim of increasing downforce. The edge of the splitter seems to have an effect on the downforce, and it could form an area of development worth investing some time in. Taking an overview of each of the additions with this plot, the overall trend has improvements in overall downforce with an expected drag penalty. The only glitch in the assumptions came with the addition of the splitter's fence, removing downforce which was all at the rear, as well as a tiny bit of drag. One last case was run with the fences removed and a lightly modified air dam to see if the downforce came back to the extrapolated gurney flap addition. The concluding case just fell short of the extrapolated difference. So there is something that the splitter fence does to remove the lift that I'll be looking at later after seeing why all the other additions work. First, a look at the front and rear lift distribution. Everything is pretty much as expected. Change something at the front and the front changes. The front and rear does have a complex interaction, mostly a product of the very rough floor that this car has. A smooth flat floor would simplify some of these interactions because the boundary layer wouldn't build as much with the smoothness. Going by these plots from under the car's centerline, the air dam creates a bit more front downforce by accelerating the air underneath the front a little bit more. The air continues to slow up until a meter before the rear axle, as a fact there is less mass flow rate underneath the car. The pressure doesn't rise anymore and decreases towards the rear. The splitter has a characteristic drop in static pressure as it passes over the surface. The front and rear lift distribution shows that it creates a significant amount of downforce. The increase in the rear is due to the air continuing to slow after the splitter. But adding a spoiler to the rear makes the rear neutral at the same time as increasing the front downforce, making the splitter more effective by helping reduce the blockage from the slowing air underneath the car. Here is the most interesting part of these modifications. Moving the air dam back at the corner to under the front bumper significantly improves downforce at the rear, which means the floor is more effective. The cost is a little loss at the front, but now there is some downforce at the rear rather than none. The plot along the centre line, the splitter has accelerated the air less, and the rear downforce is likely coming from the centre, after the midpoint of the wheelbase, at negative 1.2 metres. The plot along the y-axis, the width of the car, at negative 1, is illustrative of the difference. Adding the fence on the splitter seems to be a mistake, as it removes the total gains from the air dam modifications. This plot shows an almost identical characteristic when the gurney is added. The gurney flap recovers the losses and then some. Barely any significance in the centerline characteristics, suggesting that the removing of the fence will add 22 newtons of downforce at the rear, which it basically does with the final simulation. It wasn't just removing the fence and adding the gurney flap, but a small extension was left on the air dam. Not a strictly correct method, but that's what I'm going with. The centerline plot has a characteristic mostly returned to the original mold of the air dam, with a little difference and improvement. In terms of the front and rear split, the downforce is now 70-30, reasonable for a front-wheel drive car. This concludes the summary of the modifications. You can now decide if it's worthwhile spending a couple of hours bodging a plywood splitter and an aluminium sheet spoiler. The obvious answer is yes, which is funny because building this model and running these simulations took a lot longer than a couple of hours. The rest of this video will be understanding why the fences didn't work, or why the modified air dam did work. To start, I'll be looking at the Y plots from underneath the car. Clearly the mod is much better, even than the gurney, which is supposed to have more rear downforce. The last case somewhat restores the plot. With the total pressure or energy plot, there is something going on with the width of the disturbed air. The fence reduces the width. The streamlines of the fence pushes the air wider, so the direct effect is somewhere else. A total pressure slice from where the Y plot is taken by the purple line. As it turns out, the outwash from the fence is high and wide. Here is the streamlines. I took the Y and Z velocity magnitude slice to give me a better idea of where the flow structures were at this point. There is a clear difference, with the mod being the simplest, with one clear vortex running along the side. Where did this come from? Turns out it's the tie squirt. Which way is it rotating? On the left, clockwise. This is the answer I was looking for. The spoiler fence breaks this down and has a counterclockwise rotating vortex, pushing air under the cart, increasing the pressure. This is a really interesting find. It shows how sensitive the area around the front end of the car can be. This would also mean that introducing steering and yaw would mean that this find would change under dynamic situations. That is everywhere else outside this simulation and a car going straight. Even though the percentage changes are large at the rear, it needs to be noted that the maximum 60 newtons of downforce is 135 newtons at 45 meters per second, or 160 kilometers per hour, and is a small percentage of the 300 newtons from the weight of the car. That is not to say that it is insignificant. From a car that originally had positive rear lift and no front downforce, it can be worth up to 1.5 seconds to 2 seconds around a tight circuit, like Wakefield Park.